Um, Sorry about the other video that ended abruptly. We were trying to prove the orbit stabilizer theorem, which says essentially that the size of each orbit, so if you pick any element in your set X, the size of the orbit is in fact the equal to the index of the stabilizer of X in G. And we show that to prove that, you just show that there is a bijective map between the set of cosets of the stabilizer in G, and the stabilizer of X in G, and of the orbit of X. And the map is given by extending this coset to GX. We show that it's well defined, it's injective and surjective. Therefore, the size of this set, which is the set of cosets, is equal to the size of the orbit of X. But we know this set here, if G is finite, then this is exactly the size of G, or the size of the stabilizer. But in general, this is just the index number of cosets you have of the stabilizer in G. Okay, so that's our orbit stabilizer theorem. Now we're going to give some specific examples where we know the action. So here, the action is by conjugation. The group is acting on itself by conjugation. You can check that this is an action. The identity, of course, acts by doing nothing to X. So if G is identity, you just have X again. Okay, so under this action, the orbits have a special name. They are called the conjugacy classes. So the conjugacy class of X, which is essentially the orbit, which is just the orbit of X, under the action of G on this side by conjugation, it's just a set of conjugates of X. Okay, and the stabilizer of X, so these are the elements that fix at X. So essentially, it says that G acting on S is going to give you X, which is something like saying that GX, G inverse is just X. If you multiply on the right by G, you get what you have here. So this is the stabilizer, okay? And in this case, it's got a special name. We call it the centralizer of X and G. Okay, the class equation here is this says that you can, since we know we can partition the set, so G is acting on itself here by conjugation, so we can partition G into orbits. So there are essentially two kinds of orbits. So the center of G, so the center of a group is the set of elements in the group that commute with everything. Okay, so since we are acting here by conjugation, if X commutes with everything in the group, so if X is an element of the group that commutes with everything, then in particular it commutes with G, and you can move G to this side and then they cancel. So the conjugacy class of X in that case would just be X itself. Okay, so all those elements that belong to their own conjugacy class, so they have their conjugacy classes contain just them. Those elements are called central elements. So we collect all the elements that are like that. We call that the center of the group. It's called center of the group, ZG. And then the remaining elements, partitions, belong to their conjugacy classes, and the conjugacy classes contain more than one element. Okay, so that's what we have here. So for each, single element, you collect the conjugacy classes that's CGI. Then if an element is not there, then you form its own conjugacy classes and so on. Then you sum them up, the size of each of them, the size of this was equal to the size of the group. Okay. And the proof is just, just collect the center and then they take the adjustment, of the other conjugacy classes. That gives you the result. Okay, I think that we are ready now to prove, okay, not quite ready. So let's discuss base P expansion. So if you have, it's not necessarily prime, just take any positive integer, P greater than or equal to 2. Then if you give me another positive integer m, then this integer is called a unique expansion in base p. So it's called a unique base p expansion in this form. So what really makes this unique is that the mi's here are all greater than or equal to 0, but less than or equal to p minus 1. And the highest one, mk, here is not equal to 0. So this expansion is unique. Yeah, okay, so the only reason why we need mk to be not to be equal to 0 here is essentially to, we can use that to define what we call the length of the expansion. So we're going to call the expansion length k. Some people call it k plus 1, but we can call it just length k, okay? But of course, you can add zeros here. So when we say, okay, so this is just to make it unique. Okay, it's just that this is non-zero. That's what makes it, helps to make it unique. Otherwise, you can add zeros, 0pk plus 1 and 0pk plus 2 and so on. Okay, these conditions, this is unique. So let's prove it. So prove that this is unique, we have to prove two things. So if you have another base p expansion of m, then the length also must be k, okay? And then the mi's will be equal. Okay, so that's what we want to prove. So suppose we have two distinct expansions. So this is expansion of m base p, another expansion of base p, and we see that mk prime is not equal to 0. So the highest coefficient there is not 0. This is not 0. And they are all less than p. They are all positive, sorry, non-negative, and they are all less than or equal to p minus 1. Okay, so since this is m, this is m, they are equal. Okay, so these two things are equal, but they are two different expressions, expansions of m base p. So now what do we do? Well, we know that the mi, so let's take this one for example. We know that mi is less than or equal to p minus 1. By definition, less than or equal to p minus 1. So what we can do, if we put p minus 1 here in place of mi, then this sum here is greater than or equal to m. So this p minus 1 we can factor out here, then we have some pi 0 I going from 0 to k, but that's just going to give you p k plus 1 minus 1 over p minus 1. Okay, and that's a geometric sum, so it's going to be p k plus 1 minus 1 over p minus 1. Well, that p minus 1 will cancel the p minus 1 we had before, and so what we have is p k plus 1 minus 1. So that means that m, so since m is less than or equal to pk plus 1 minus 1, then m is strictly less than pk plus 1. But also, look at this expansion here, because we assume that mk is not equal to 0. So mk, remember, mk pk is part of the summation we have to get m. So m is strictly, well, not necessarily, but m is greater than or equal to pk. Okay, so m is between pk and pk plus 1. We do the same calculations here, and we conclude that m is between greater than or equal to pk prime and less than pk prime plus 1. Well, this is the only way this can happen. Yeah, the only way this can happen is if k is equal to k prime. Okay, so now we conclude that the k and the k prime must be equal. What is left to show now is that the mi's are equal. So mi here is going to be equal to mi prime for all I. So assume that m has two expansions where the same length k, so we have that. So that's m is equal to this, equal to this. If we subtract, so we can subtract 1 from the other, subtract this from this, you get 0. Now, what we want to show is that mi minus mi prime for all I is mi is equal to mi prime for all I, which means that this quantity here is also 0. But supposing that was not the case, then there is some, let's take j. So let's j be the largest index such that mj is not equal to and j prime. So for higher j's, these are equal, so this number will just be 0. So we take the highest j for which this is not equal, and then we move the remaining part of the sum. So the remaining part of the sum goes to this side, and that gives you what you have here. So if you look on the left-hand side, you can see that pj divides this. This is something times pj. So pj divides this side. However, if you look at this side, we can take the absolute value of this. So we just have the absolute value of this. Now look at this number here, mi minus mi prime. This number here, so each of them is less than or equal to p minus 1. So by here, therefore their difference is also less than or equal to p minus 1, an absolute value. So we can factor out that p minus 1 here, and also do this summation again. So if you sum I going from 0 to j minus 1 of pi, as we did before, you're going to have pj minus 1 over p minus 1, and p minus 1 will cancel that p minus 1 here. So you have that this is less than or equal to pj minus 1, which is less than pj. So this quantity here in absolute value is less than pj, so pj does not divide it, but pj divides this left-hand side, which is a contradiction. Therefore, the assumption that mj was not equal to mj prime was false. So we conclude that mi is equal to mi prime for all others. Okay, so now we are back to our theorem. Let's now try to prove this theorem. So we have let p be a prime, and m and n greater than or equal to 0 have base p expansions. Okay, so again, this is a base p expansion of m. Okay, and then this is the base p expansion of n. So here we're not putting any conditions on, except that mi and ni are greater than or equal to 0 and less than or equal to p minus 1. We're not insisting that the highest number mk here is non-zero and this is non-zero. So essentially one of them would be non-zero. What we do is to make up the other ones by adding 0 so that they all, end at p to the power k in both cases. Okay, so that's so suppose this one ended at pk minus 1. We have to add the pk by and then put 0 here, so to make it complete. It is still, if you ignore the zeros, then this is still unique. So yeah, okay, it's still unique. So up to addition of those zeros. Okay, so that's so another way to say it, if you wanted the length to be exactly, if this is the length, then it's still unique. Okay, it's still unique up to in that sense. So that's fine. So this expression of m and okay, so these base p expansions are unique in the sense that if you have any other expansion of m of this length, okay, then you will have exactly the same mi's. Okay, so it's no longer unique in terms of the length because I can keep adding zeros, but in terms of up to pk here, if you fix pk here, then if you want both of them to have length k, then it's gonna be unique. Okay. Anyway, so the main thing here is to show that the size of m choose n is just the product of mi choose ni, I going from 0 to k mod p. So if you want to compute this combination here, m choose n mod p, then the answer is just this, which makes it really easy. So if you can obtain the base p expansion, which is really easy to write down, then you can calculate what m choose n is mod p. Okay, so let's do an example, just a quick example. If you take m to be 14, then the highest power of 3, so we're looking at base 3, the highest power of 3 that is less than 14 is 2, so that's 9. Remainder 5, so that's 1 times 9 plus 5. The highest power of 3 that is less than 5 is 1, so that's 1, 3. And then remaining 2, which is 2 times 1, which is that. The same thing with 5. So you can see that the highest power of 3 to the power 2 is 9 is more than 5. So it's going to be 0 times that. Then 3 to the power 1 is less than 5. You have 1 of it and then 2 here. Okay, what this theorem is saying is that M combination N mod P, which is 14 combination 5 mod 3, is equal to 1. And how do you get this 1? Well, you do 1 combination 0 times 1 combination 1 times 2 combination 2. And the answer will give you 1. So that's the answer. Okay, so let's go back to our proof. The proof is by group action. So we take our, we remember we want to compute M, choose N. So we take a set of size M, okay? And then we obtain the base P expansion of M in this form. So what this is saying is that to form M, you need M naught blocks of 1. So M naught blocks of 1. You need M1 blocks of size P. So a block with just a set, a subset. Okay. So you have this number of elements. And you sort of break them into blocks of size 1, a subset of size 1, subsets of size 2, subsets of size P, and so on. So to get M, you have to cover the whole M of them, you need M naught blocks of size 1, M1 blocks of size P, and so on, MK blocks of size PK. Okay, for each I, so I going from 0 to K, we create MI disjoint blocks BI1 to BI-MI of size BI. So if you focus on this case, for example, you're going to create M1 blocks of size P. Okay, so for example, if I is 1, so you're going to create B1 up to BM1, which are going to be blocks of size P. And then you do that for each of the I's, and then the set M is just going to be first of all, you take the disjoint union of the blocks for each I, and then you take the disjoint union for I going from 0 to K. Now, for each block, for each of the Bij's, for each block Bij, remember this Bij is got, so the I here is just counting the number of blocks. So the second component here, 1 up to Mi, is just counting the number of blocks, and I is just giving you a saying that these blocks are of size Pi. So for each block of size Pi, what you will do is you will let this cyclic group of order Pi act on this block. Remember, this block is a set that contains Pi elements. You're going to let this cyclic group act on this set by permutation. So you have to somehow fix an ordering of the elements in Bij, or you can choose this set so that it's an order. So for example, you can choose 1, 2, if it's of size 3, you can choose 1, 2, 3, or 3, 4, 5, or 5, 6, 7 in that order. In that case, there is a clear permutation that just permutes the set. Okay, so for example, if you choose 3, 4, 5, you can take the element 3, 4, 5 of the symmetric group of order 5, and it's just going to permute. So the 3 cycle 3, 4, 5 will just permute that set. Okay, anyway, let this be a cyclic group of order Pi, which is acting on this set by permutation. By cyclic rotation. So it's rotating it cyclically. So for each block, you have this cyclic group acting on the block, And then you can define G to be, again, the direct product of each of the cyclic group and then the direct product of that. Okay, so for each level, so for each level, let's say level these blocks, for each of the block you have a cyclic group of other pi acting on this block, and then for the entire set you have this group here, which is the direct product of the direct product acting on that. Okay, so that's going to be our group G, but we have to define so we have a group G, which is the direct product of cyclic groups, which is just direct product of cyclic groups, and we have a set X. S is going to be the set of subsets of M. So remember, M is 1 to M. We take subsets of size n. That's going to be our X, and G is going to act on X. So how is this action defined? Well, if you take a subset which is of size n, which is here, the way the action of G is just the set of G acting on X. Well, G is an element here, so how does it act on X? Well, X is an individual, each element so for each element in X, G acting on S is just Gij X if X is in this block. So essentially what it's saying is that if the element, so look at your set S, you pick an element which is in that S. Well, if it belongs to, say, this block here, then there is a cyclic group. So if it belongs to this block, then this cyclic group is what? So the action of an element in the G in the group is just the component of that element that lies in this cyclic group. Is what will act on it. Okay, that's it. And the action is just by, again, as we said, by rotation. It's just going to rotate it to the next element. Okay, so that's how we define the action. I hope that's clear. But the G acting on S is just G acting on the individual elements. And how does G act on individual elements? Well, it depends on where the element, which block the element belongs to. If the element belongs to this block, then this is the action is just the rotation in that block. Okay, now remember that G is a P group. So the way we formulated G is a direct product of cyclic groups of other pi, so it's a P group. The stabilizer is a subgroup, it's also a P group, so it's a P group. P to some power divided by P to some power is P to another power. So which means by the orbit stabilizer theorem, the size of each orbit is a power of P. Now remember, we want to take the mod P. So if the power of P is the power is not 0, if it's something bigger than 0, then if you take mod P, of course you get 0. Okay, so if it's 0, if you take mod P, it's just 1. So if we are taking this number mod P, then the only thing that will survive, so this will survive only if that orbit has only one element. Okay, so modulo P, only orbits of size 1 contributes to this number. So what is this number, by the way? So this is the number of ways to choose n elements from m elements. Okay, so another way to say is that this is the size of the subsets of size n of a set of size m, which is essentially what we call X here. So we have X here, which is the subset of m of size n. So the size of this set X here is just m choose n. Now we want to compute m choose n mod P. Well, if we go back to our theorem here, which is the class equation, it says that the size of G, so size of G is, so here G is acting on itself by conjugation. So that's the action. But it doesn't, this theorem, this result is actually true in general. So if G is acting on a set, it's the same thing with well, let me go back. It's just the same thing as this theorem here, saying that the orbits partition the set. So what we do is we have two kinds of orbits. These orbits, there are some orbits that contain more than one element, and then orbits that contain exactly one element. So in the case where the group is acting on itself by conjugation, we call these orbits where, so those orbits that have only a single element, we group them together, they form, those elements form the center of G, and then the other orbits are here. So that's what we're doing here in this case. We are, so if orbit contains only a single element, then of course mod P. So again, this is the size of the set X, this is the size of set X. And then, so that's going to be the sum of the, so the elements, the size of the set of elements that belong to their own orbit. So that's the fixed subset of G. And then the elements that, the orbits, the sum of the sizes of orbits that contain more than one element. But we said here that the orbit, the size of the orbit is a power of P. So if we take mod P, all those ones will give you 0. So the only thing that you have left is the fixed subsets under all of G. Okay, so now this is what we want to calculate. Now, based on the way we define the action, you can see that if, you know, for a subset to be fixed, then it must either intersect a block trivially, so there is no intersection, and the intersection is empty, or it contains the whole orbit. So the point here is that a fixed subset cannot contain part of an orbit, part of a block. If it contains part of a block, then because of the rotation, each element is acting by rotation, it's going to rotate those elements and move some of them outside that set. So it has to contain the full block, or it doesn't contain anything at all in a block. So that's this case. So essentially, this is saying that the fixed subsets are going to be just union of blocks, just union of those blocks that we define. That's the only way that a set can be fixed, if it's a union of blocks, or it's an empty set. Furthermore, exactly n blocks must be chosen at level I to match the base P digits for n. So again, we want to choose a set of size n, and if you want to express n in blocks like we have done in base P, there is a unique way you must choose ni blocks of size at level I. So blocks of size pi, you must choose ni of them. There is no other way to form n to get n. Okay, so at this level I choose ni out of the mi blocks, which is this number here, and you have to do this independently of, the choices are independent across all levels, so the fixed subset is just the product of ni. That's what we wanted to prove. Okay, I'm just going to do a quick example again. I think we've seen this example already at the beginning. M is 14, N is 5, P is 3. The expansion of 14 base 3 and expansion of 5 base 3. And then, so this is saying that if you do 14, choose 5, mod P, mod 3, it's just 1. Okay, thank you.